law, sponsored by the New South Wales government. Eugene is probably one of the most experienced data scientists in Sydney, but maybe not. There may be somebody else here. Put up your hand if you are. I'd like to challenge it. Eugene is not only a data scientist, he's also a philosopher, and hence tonight's talk is titled The Zen of Predictive Analytics. So I think this should be a very interesting philosophical digression away from source code. So I'd like to welcome Eugene up to the stage.
Well, thanks for that terrific introduction, Rami, and wow, big crowd. Standing room. Just out of interest, how many of the people in this room are working with predictive modelling or machine learning or regression modelling right now? And how many have worked with it in the past? How many would like to work with it? And how many have to manage people doing this kind of thing? Anyone? Oh, one, two. Excellent. All right. Well, hopefully you're all in for a bit of a treat. Yeah, that's a slide with my name on it. And let's get on with the show. So before we talk about what I'm going to talk about, I'm going to use this opportunity in front of all you good people to do some promotion, including some self-promotion. So here you are, captive audience, and I'll tell you about all the things that this talk isn't about, hopefully very quickly. So the things I want to mention are, first of all, R, which I'm very passionate about, and the Sydney Users of R Forum, which I run, and will encourage you to join. Something called Analyst First, which I founded together with Stephen Samuel over there. So if Analyst First is of interest to anyone here, talk to me or talk to Stephen at the end of this talk. And I'd also like to tell you about training, mentoring, and coaching that I do in analytics, data mining, and R. So first of all, Sydney Users of R Forum, we're just one shy of 500 members as of today. We have 499 members. So I'm counting on at least one of you to sign up and tip us over that magic number of 500. We have regular meetups. We meet about every month. There's a meetup coming up on the 30th where a very dynamic and interesting presenter, Sebastian Duchesne, will be telling us about the survey analysis and experimental design capability within R. We also do things like run study groups, particularly regular study groups on an introduction to R. And currently there's a study group with Sebastian working through the Machine Learning for Hackers book by Drew Conway. We've also had a study group with those daring enough to try out elements of statistical learning, which is not an easy book by any stretch. There's a screen cap of our meetup page, as you can see, 499 members. Then there's R itself. I should mention that R is a pretty nifty thing to use. Who here has used R? Who'd like to use R, but possibly thinks it's a bit scary? Well, do join the user group. Now, two things I'll draw your attention to very quickly. Well, two. I always agree. It's like that Spanish Inquisition Monty Python skit, if anyone knows. The number keeps increasing. So three things I'm going to tell you about. First of all, if you don't know that R is absolutely amazing, do the following. Do a Google image search for ggplot2. ggplot2 is R's phenomenal graphics library, and what you see are all examples of the kinds of graphics you do in R. This is my favorite way of selling R as a real business solution to clients. Here's the R webpage from which you can download and start using R in like 5 minutes. And if you're still not convinced, there's this site, which is pretty nifty, called The Popularity of Data Analysis Software, and it tells you things like surveys keep showing that R is the most popularly used data analysis tool, more popular than, according to these surveys, than all the commercial tools. Also, R is more popular almost than all the other tools combined on Kaggle in terms of its use, and even more popular in terms of use by champions, and that's saying something. So do get into R if you're at all interested. It is good stuff. Now, do join SURF, and just play with R. Another thing I want to tell you about is Analyst First. So today I'm going to be telling you about predictive modelling. Yes, it's going to be a philosophical talk, but it's going to be a philosophical talk still about a technical topic. There are a whole lot of strategic, cultural, organisation, human issues in analytics. I think they're actually the biggest challenges in our industry. And Stephen and I created an institution, an organisation called Analyst First to address these. If you want to find out more, you can go to analystfirst.com and have a look at the core principles and the What is Analyst First page. We should also point out that it's now an international organisation. Most recently we've established a chapter in Washington DC, which takes us to, 11 cities in 7 countries, I believe. There's a list there. Finally, a bit of shameless self-promotion of my analytics training courses. We all have to eat. Part of the way I do so is by teaching this kind of stuff. And the current suite of public courses which run regularly in Sydney, Melbourne, Canberra, and starting now in Singapore, things like predictive modelling, data mining, more basic aspects of analytics, data visualization, and the latest application course on forensics and fraud detection, which is about to roll out in Canberra and Sydney. I do these as public courses, but I'm also happy to do in-house courses, pre-prepared or customised to your needs. I also do informal, high-level coaching, mentoring, and helping people set up their analytics functions. All right, enough with the self-promotion, on with the show. So what you're going to get today is a little talk I do that's actually part of my predictive modelling course, and I call it the Zen of predictive modelling. Now, I tell people with full heartfelt honesty that this is the most important part of the course. I find that my students tend to be split into those who say, yes, this stuff is absolutely amazing, and those who say, this is airy-fairy abstract, why don't you show us more algorithms, please? In fact, I think this is the part of the course that tells you exactly why being shown more algorithms is probably what you don't need at that point. If you think you need algorithms, you probably don't need algorithms. I think this is something that every user of predictive modelling should know, and it's probably something they should know before they start learning the deep technical stuff. And more importantly, I think this is the stuff that the managers of analytics functions should know, even if they ignore the technical stuff. So I believe that this stuff, which is commonly not taught at all, should be taught first. A lot of this is also open secrets that people in the know, people who have been doing this for a long time, actually already know. But again, you don't see it discussed as explicitly very much. And why do I want to do this? Well, I want to save you folks a whole lot of time. This predictive modelling stuff, it can be tricky and you can go down a lot of rabbit holes. I want to give you the big picture so you focus on the stuff you need to focus on, to see the forest for the trees, to see the important features, make the right decisions, and get real value out of predictive analytics if you're using them in business applications. So the first thing I'll do is I'll start by presenting what I think is the right point of view. So I accept that in life there are many different points of view, but I'm one of these people that also believes that some of them have to be right and some of them have to be wrong. Some of them have to be useful, some of them have to be less useful. Now I've got a whole lot of jargon on this page. For those of you who don't know what any of these terms mean, don't worry, that's okay. We'll get back to more general stuff later. For those of you who do know what they mean, this might be a good case right now to possibly change your views about it. Now what I find is that if I present people with these 3 different machine learning methods, Kahuna neural network, backpropagation neural network, and CARP decision tree, and I ask which one is unlike the other 2, can I have some suggestions from the audience? Which is the odd man out? Anyone? Okay, who thinks it's the Kahuna neural network? Hands up. Who thinks it's the backpropagation neural network? And who thinks it's the CARP decision tree as the odd man out? Really? Okay. The odd man out is in fact the Kahuna neural network. The red herring is that the first 2 are both neural networks, but that's kind of irrelevant. That's a false categorization, well not false, but unhelpful categorization. In fact, the first one is an unsupervised learning method. and the second two are both supervised learning methods. The fact that they're completely different methods doing the same thing in a completely different way is less important than they're doing the same thing. They're more or less solving the same business problem. They're more or less working towards the same outcome. The Kahana neural network, which is an unsupervised learning method, which used for things like outlier detection and clustering, does a fundamentally different job. So the point here is that for a lot of people have the wrong taxonomy in their heads. And I'd like to reinforce here this taxonomy of predictive modeling or supervised machine learning as being a family of fundamentally similar things. And if you understand that they're fundamentally similar, you'll stop getting lost in the details. So in this case, the cart decision tree and the backprop neural net are predictive models, and the Kahana neural net is. Now here is another one. We've got a cart decision tree, which is a single decision tree, which we've got a random forest, which is a whole bunch of decision trees, complex decision tree based model, and we've got a support vector machine. Now, this problem's a bit more difficult. All three are predictive modeling methods. Which one's the odd man out? First of all, who's heard of all three? Who actually knows what I'm talking about? Not a lot of hands. All right, here's the important thing, and the important thing for those of you who've never seen this before, some predictive modeling methods are very simple. And we use those simple methods to try to understand things, to try to explain systems. They're not the best for predicting stuff, they're the best for explaining stuff. Other predictive modeling methods are extremely complex and extremely accurate. And the point here is that we have one that's relatively simple, which is a single decision tree. And there are two which are very complex. The random forest and support vector machine are very complex. We'll use the second two to get good accuracy, good predictive accuracy. We'll use the first one to tell a story. Those are the two uses we put predictive models to. Understanding that those two uses exist is part of this presentation. Understanding the difference between simple and complex models is another part of this presentation. And finally, we have the same question again. We have our friend the backpropagation neural network. We have the linear model. And for those of you in the know, linear models are a trivial example of backpropagation neural nets. And we have a cart decision tree. Now, I'll get cut to the chase here. The linear model and the cart decision tree are both simple models which we can use to tell a story. The backprop neural net is the complex model we use to forecast accurately. They actually do the same job. They're all supervised predictive methods, but they specialize differently. All right. The other point of this story is I want to reinforce that when we use predictive models, we're looking for 4 different qualities in our models. And we're usually trading off between those qualities. Now, as it happens, some of those qualities go together, and some of these qualities are actually completely opposed. I foreshadowed already that we use simple models when we want to tell a story. So we use linear models, generalized linear models, decision trees to tell a story. And we use complex models when we want to predict well. That's not entirely true, as I'll discuss in a minute. Because one of the reasons we may want to be doing modeling is, as I said, prediction. And the way we know we've got good prediction, our KPI, is something called out-of-sample accuracy. So for those of you who've never done any predictive modeling before, the way we know a predictive model is good is we build a predictive model and then we get it to predict with data where we know what the output is, but we haven't put it through the model before. We see how the model does on things it hasn't touched before and see if it's actually learned something useful. A model that predicts well on such data is said to have good out-of-sample accuracy. And those complex models I mentioned with the big names, the support vector machines, the random forests, the backpropagation neural networks, they're all looking to give you good out-of-sample accuracy. That's why we use them. Now there's another thing we want sometimes, because life is a very complex and changing thing. Has anyone here worked in or is currently working in financial trading or a hedge fund or something similar? Has anyone done any trading? Okay, one hand. The thing about trading is, what makes it scary, and it's not just trading, this applies just about anywhere we use machine learning in the real world, life changes. The situations we're modeling change, the dynamics change. Everything changes and models lose their effectiveness. The underlying system, the thing that the model is built to represent, changes over time. And your model needs to be robust, needs to not fail when these changes occur, or not fail too quickly. Now, the thing is that the most accurate methods that I've just mentioned, these really whiz-bang sophisticated methods, tend to be the ones that break the most quickly when things change. So sometimes when we want good predictive accuracy but it's in a changing environment, we will still want a simple model. So simple models are good for telling a story, and simple models are also good for weathering the rough seas of changing environments, like financial models or customer behavior or risk behavior or fraud. It all changes. Now, I've mentioned interpretability before. That's the insight stuff. Sometimes we're not interested in using our model to predict stuff at all. Sometimes the model isn't there to be used in the operational sense as Quinton was describing, where it's put into a real-time system like Storm to score millions of transactions per second or customer records as operational analytics methods are done. Sometimes we build a model because we want to see what the drivers are of certain behaviors. We want to tell a story which will help us design a better product, which will tell us whether we want to enter a particular market, which will tell us what our advertising campaign should look like. So we use models for insights, and then we want models to be interpretable. Sometimes we also want it to be interpretable because you like the model, but senior management doesn't trust it and thinks it's a black box. In fact, I've heard the expression black box in a meeting earlier this morning, where people, even building models for prediction, had to justify them to non-technical people. And interpretability becomes important, and you might need to use a simple model for that purpose. And finally, we have implementability. So back to the situation Quinton discussed, the real-time implementation. Sometimes something like a random forest, which can often have more numbers in it, more actual sheer numbers in it than the data set it's trained from. They can be enormous. They're often not implementable for real-time, low-latency applications. And sometimes we want our model to be simpler, and we're willing to sacrifice accuracy for simplicity. So these are all different criteria, and they're often in conflict. Now, the interesting thing is that out-of-sample accuracy is the odd man out. I think that models that you build to develop out-of-sample accuracy are models that are fundamentally different than models that are simpler and focus on the other three. It's not really a four-way split, that's the good news, it's more of a dichotomy. There are the simple models which tell stories, are robust, and are easier to implement. And then there are the more complex models which really nail the underlying behavior and give you fantastic predictability as long as things don't change and as long as you don't ask them to explain themselves too much. I should also reiterate again this question of why we build predictive models, because there's actually a third reason. So I've mentioned two reasons. I said that we might be building predictive models and indeed doing other kinds of analytics for predictive insights. And again, we might be building predictive models and doing other kinds of analytics for operational prediction. Oddly enough, you might be using outlier detection models or our friends the Cahonen nets for operational analytics. They're not strictly predictive, but they have their place as well. Wow, this philosophy stuff isn't for everybody. There is also a third use, and this is what-if analysis. Now, what-if analysis is relevant to the sort of stuff some of you are doing. How many here are doing A/B testing? I'm sure a lot of hands are going to go up. Well, a few hands. Who here is doing multivariate testing? So if you're doing multivariate testing, you'll want to be doing what-if analysis on your data. So you're not just going to be looking at insights, like big picture driver insights. You're not just going to be scoring data with real world data. You're also going to be putting in hypothetical data to see what hypothetical outcomes are going to be to produce optimal outcomes, optimal conversions on your website and optimal traffic. So we've talked about a few of the corners of the issue we're going to discuss. Let's jump into the meat of it. What I want to talk about is the opposite of what a lot of my students want me to talk about. A lot of my students want me to go into the details of this algorithm or that algorithm. I want to talk about what makes all algorithms fundamentally the same. And it's only when we talk about what makes them fundamentally the same that it starts being meaningful to talk about what the differences are or why you should care about it. We will get into a few of the differences later, but let's start with what's the same. So for many of you, this will be your first introduction to predictive modeling. How many of you have never really studied any predictive modeling at all? For whom is this like first ever? Fantastic, that's great. Okay, I've got you guys at the right time. You're very lucky you're here. It could be worse. All right, so here's the deal. Predictive modeling is something we do where we have some sort of data set which has many, many fields, which are our predictors. For example, let's say we're looking at customer behavior, so we have customers' ages, their gender, their income, a lot of things we know about them, and we have some sort of outcome we're interested in. And the outcome may be whether the customer does and doesn't buy our product. We have lots and lots of such customers, we have a whole lot of these predictive fields, and we have one outcome. And the outcome is just a yes or no, they did or they didn't buy. Now, what we want to do is, based on this data, see if we can find some kind of general rule, some kind of sustained general rule, a set of rules that relate to these predictors, these gender and age and income and occupation, whatever else, demographics, for example, to the outcome. And on that basis, to grab people in the future and see if we should target them to sell our product, to figure out who we should target in the future. So we call this data set of predictors and outcomes, we call it the training set. We probably want to have an additional data set of targets and outcomes that we're not going to use to build our model. Remember I said we want to test our model on data that the model hasn't seen before. That's how we know that the model works, because it'll give us good scoring on data it hasn't seen before. And then what we do is we build this model, and we build or fit this model to minimize something called an error function. In other words, we want to get as few of those classifications, in this case customer classifications, did they or didn't buy, incorrect as possible. We want to minimize the number incorrect. We want to minimize it on the training set, we also want to minimize it on the cross-validation set. And there is something called overfitting, where your model sort of rote learns and it looks really, really good on the training set, but it's absolutely crap on the cross-validation set. In that case, it's rote learned every example, but it hasn't learned the general rule, and it's useless as a deployable model. So this word overfitting, remember it, it's a problem, and it's something to worry about. All predictive models have this. This is something that applies to all predictive models. I don't care which model you're using. They all provide information on the relationship between the predictors and the outcomes. That's what a predictive model is. We can use all predictive models to score new data. So with this predictive model, if we get a new customer coming along, and we know their age, and we know their gender, and we know their income, we know all those predictors, we don't know the outcome, we can actually estimate the outcome. We can estimate a probability of that person being a buying customer. That's called scoring. All predictive models do that. Now, all predictive models can be deployed in IT systems. They all end up as rules or a formula. That's the idea. The outcome of this modeling exercise is this formula or set of rules we call a model, and you can deploy it, or they can be interrogated for insights. As I said, some are harder to interrogate for insights than others. Some tell a very simple story, some no human being will ever understand, but they all tell some kind of story. Actually, come to think of it, all of them can be interrogated for certain insights, even the more opaque ones, if you know what you're doing. The other thing is they're only as accurate as the data allows. I've had a lot of clients complaining that the model isn't accurate enough. And when I say to them, okay, so what are you doing? Oh, we're going to try this method now. I said, okay, fine. My bet is that's not going to help you. It's going to be more or less the same poor accuracy. This is only, your data has an inherent relationship between the predictors and the outcome. Now, some models capture it better than others, but ultimately, you can only do so well. Ultimately, there's just a limit to that relationship. And maybe there's no relationship at all. Once or twice in my life, I've come across data where there's no relationship. Actually, if you really want to find data with no relationship, or almost no relationship, look at finance data. Because the only question there is there nothing, or is there very, very little? And all models provide a fairly accurate estimate of how well they will predict a new data. So the really good thing about predictive modeling, the business value of predictive modeling, is that they come with their own ROI. So a predictive model won't just give you these insights and won't just give you this fantastic scoring ability. It'll actually also give you an estimate of how much money it's going to make you. It will tell you how well you can expect it to predict on new customers. So it'll say, look, I'm going to get about 60% of the customers that I'm hitting, and I'm going to get them right. And given that it costs you this much to contact them, and given that you're going to make this much money every time you get one, you're going to probably make about this much money. It's a bit more complicated and it involves something called the lift curve. It's not too complicated. It's actually a very interesting story. It's a beautiful thing that comes with its own ROI. I wonder if this is why marketing departments love it so much. So, what else what do all predictive model insights have in common? I mentioned before that you can actually use all predictive models to tell a story, including the more complex ones. So let's talk about what all insights have in common. Now, linear models tell a particular very simple story, and decision trees tell a particular very simple story. But there's a story that all models tell, and they all provide variable importance measures. Any predictive model can tell you which predictors matter and which predictors don't matter too much. Any of them can do it. You have to know how to grab them, of course, and some implementations don't have it for some models, but they can and they should. And if you talk to someone in the know, they can find a way to tease it out from any model. Particularly if you're using a toolkit like R, where you're free to code around the development. You can plot predictors versus outcomes of any model, and that turns out to be an extremely powerful method of gaining insights. All models have variable accuracy measures. All models tell you how accurate they are. And all models can be resampled to give you more robust measures of accuracy. Now, there's also something that all model predictions have in common. So all models make numeric predictions. They either estimate amounts if you're doing what's called regression modeling, so you might be estimating the amount of money you might lose on a credit default or the size of an insurance claim. Predictive models are used to estimate those amounts. Or you're estimating a probability, you're estimating the likelihood of a customer buying, or likelihood of a customer churning, or likelihood of a customer clicking through and converting on your website, and that's a probability. They're both numbers. Models estimate numbers. All predictions are applications of some sort of underlying model. That underlying model is deterministic. So some predictive modeling methods have randomness in them in the way they develop the model, but none of them are random in the way they generate values. They all guarantee to generate the same value each time. They're just a formula or just a set of rules. We've talked about similarities. Now let's talk about the ways in which predictive models may differ. So one difference is classification versus regression. So there are models, as I said, where you're classifying apples and oranges, buyers and non-buyers, churners and non-churners, fraudsters and non-fraudsters, or what's called regression, where you're estimating an amount. So that is a difference, and there are a minimal set of issues around recognizing that difference. There is the difference of accuracy of operational analytics and predictions versus the value of insights. There is the difference between static out-of-sample accuracy against stability. There is the difference between deterministically fitted models like decision trees, where every time you fit a decision tree to a data set, you'll get exactly the same decision tree, versus randomized models like backpropagation neural networks or random forests, where each time you build a model, the model will be slightly or even not so slightly different. In fact, one of the criticisms of backpropagation neural nets is you can build quite different models each time due to different starting conditions. The insights, the kinds of insights can be very different. The insights a decision tree gives you are very different to the insights that a generalized linear model gives you. They can differ in their structure and complexity. Obviously, the model assumptions differ. Structure differs. Some can overfit, like neural nets and boosting models can overfit. Linear models are unlikely to overfit because they're simple. Random forests won't overfit for theoretical reasons because they're based on bootstrapping. So overfitting is more of an issue for some, less of an issue for others. Overfitting, remember, is what happens when predictive models rote learn. You don't want them rote learning, you want them learning something general about the system so you can apply them later and tell you a good story. Some obscure models, like k-nearest neighbours, are actually metric dependent. Most aren't, and that's a mathematical condition that some of you may know about and the rest of you don't worry about. Also, some predictive models are very sensitive to things like missing values and have trouble with things like categoricals and require you to rescale. Like neural networks are horrible because you have to do a whole lot of hand preparation and you have to really treat your data with a great deal of care. Tree-based methods, they don't care about missing values, they don't care about categoricals, they don't care about anything, you just dump the data in. So let's talk about what it takes to become a master of modelling Kung Fu. We've discussed the basics. I would say that as you're starting out, it's okay to think of predictive models as black boxes. So don't worry too much about what's in the box. Do be more of a computer scientist and less of a mathematician when it comes to the details of a predictive model. Your focus should be on the data, not the model. You should spend most of your time thinking about the data. You should know what models do. You should have models that you trust, and you should always be thinking about what data you have and what the data is doing. Now, focusing on the specific characteristics of the model is okay, but you do that with a pro. I always suggest that people start by having in their toolkit one really accurate model, like random forests, and one really good interpretable model, maybe an R-part decision tree or generalized linear models, maybe both. If you just have those three tools, random forests, decision tree, generalized linear model, in your toolkit, you're going to be fine. That's a good starting point. And if all you do is use random forests, which is extremely accurate, extremely powerful, and also extremely easy to use, if that's your only tool to begin applying your predictive modeling, I think you'll do pretty well. Because it lets you focus on the data and stop worrying about the model. So do master an adequate tool. Just pick one tool and become really good at it. And then empty your mind of the tool. Don't think about the random forest, think about the data. Think about what it's telling you about the data. Meditate on the data is the message. So what do we mean by meditating on the data? Do start with a highly accurate non-parametric model, and random forest is one. This is single decision tree is not so bad either. Pick a model where its accuracy is close to theoretical accuracy, and something like random forest has that characteristics. It's true that Kaggle competition winners can do a fair bit better than you, but you're not trying to win a Kaggle competition, you're trying to become handy and familiar with predictive modeling. You're taking the first step. This is about the first step, not the master step. And believe me, the difference between where you're at and where you're at if you're using random forest is much bigger than the difference between you using random forest and the world Kaggle competition winner using deep learning. So make that first 80% jump, don't worry about the remaining 20% for now. Once you're comfortable with what you're doing with building a model, forget the method. It's just a tool. You just have to be able to trust it, you have to know that you're using it, your focus is on the data. Each predictor you've got, each field you've got in the data has its own potential unique value. Your job is to measure that value. Find out how much predictability, how much value, how much story there is in each single predictor. Measure it. Each predictor could be masked by other predictors. Find out how the predictors relate to each other. Check the relationships in the data between your strongest predictors. And this is where things like single decision trees can help you tell that story as well. There are three different ways in which a predictor can be important, and they're actually theoretically quite different. It's important to understand the differences. There's the unique contribution of each predictor to the accuracy. There's the individual predictability of each predictor when you just include that, when you take all the other predictors out. And then there's the influence of each predictor in the model. They're actually three different things. If you're a raw beginner, none of this will make sense to you, doesn't matter. You will want to chase me and grab these notes and reread them a year from now after you start the modeling. It will make more sense. So when you're trying to master data, do focus on the data, have a technique like random forest that's reliable, and try to understand what your predictors are doing. Visualize their effects. See what they do, holding some predictors constant. And then build an interpretable model at the end to tell the story of what's going on in the data. Now, if you want to get more accuracy, if you're saying my model isn't accurate enough, the thing you need most is more predictors. You need more data. The thing that's going to make your model more accurate is more data, particularly better predictors. There is no substitute for better predictors. If you're using something like random forest already, you're not going to get a whole lot more accuracy from moving to support vector machines or even moving to deep learning. You may get lucky, you may even get 5%, heck, you may even get 9%, but you're not going to get 100, you're not going to get 50% more accuracy. Now, playing around with esoteric models, playing around with different model families, that's what everyone seems to want to spend their time doing when they're starting out with this stuff. I want to save you guys time, and I want to encourage you not to worry about that. That is not the main game. So the most important improvement you're going to get is if you get new predictors in the data. There is probably information in there that you haven't captured yet. Go and find it. And there's also information in there that you've abstracted out. So for example, there may be relations between individual records, which you can capture using sort of social network analysis and demographic grouping. There are a whole lot of things you can do to squeeze more value, even out of a single data set. You can derive fields from a single data set that will give you more information, but you have to know what you're doing. Now, there are illusions on the path. There are things that are going to give you just a headache and a waste of time. So trying to find the right model family and then giving presentations where you say, well, we do retail modeling and we find that support vector machines of this particular kind are the best thing for retail. I think that's garbage. There is no right model family for right applications. Every data set is different. And chasing the right model family, I think, is a waste of time. Also, I found a lot of people, once they go down this path, they keep saying, I said, how's your model? They say, oh, we're still trying to get our data right. We're still preparing our data. And this is like 6 months later. And I said, well, how many models have you built? Oh, none. You should be modeling straight away. Don't wait to get all your fields right. Model with the fields you have. Start building your models straight away. If some fields take time to prepare, fine. You can bring them in later and you can measure how much value they're actually adding, how much accuracy they're adding to your modeling. Trying to figure out what your target should be. So I've had clients say to me, oh, we still don't know what our target should be for our modeling. Well, that's a fundamental business problem. That's like saying, I don't really know what I'm doing this thing for. Okay, well, let's have a conversation about that. That shouldn't take 6 months. That should take about 2 hours worth of very serious thinking about what problem are you trying to solve. Maybe you shouldn't be using predictive modeling at all. That's fine. But it's important to be clear. And this is often in the context of people being very enthusiastic about trying to improve their models without actually having any idea what improve means. They don't have any idea what they want. They just want to be happier. We want to feel more sophisticated. We want to be happier. We want to improve our models. This can happen. So the Sun Tzu, the sort of strategic philosophy side of modeling is you've got to be prepared. You've got to know why you're modeling. You've got to know what you're modeling and for what purpose. You've got to particularly know what your target variable is. Are you trying to figure out who your customers, who your buying customers are? Are you modeling buying behavior? Are you modeling churn behavior? Are you modeling fraud? Are you modeling conversions? Have a clear behavior in mind. Know what you're modeling. Do not hesitate. Model with the data you have and model straight away rather than waiting for the perfect data set 2 years from now. Messy data is the usual story. Everyone says our data isn't perfect. That's life. Model with messy data is better than no data at all. Do use the right measures. Are you using mean squared error on classification problems? Are you using raw classification error when you should be converting it to some sort of dollar-based figure? Ultimately, you want to be measuring ROI, and you need to be making your measures commercially relevant. Know the connection between the model and your business. Understand why you're doing it and what value it's going to give you. Do evaluate and interrogate your model to deliver that value. Always question the value that the model is bringing. Even if it brought value in the past, ask if it's still going to bring value or what you need to bring more value. Always question. Always be ready to suggest analytics as a bit in business use. There's always more uses of it than are currently being made now. And don't assume that your client understands what to do with the model, even if they say they do. The strategy and tactics side is always ask yourself why you're building or rebuilding a model. Is it strategic? Are you building a model for strategic reasons? What is going to be done with the insights? Who is going to use those insights? How can they deploy those insights in a product development, market entry, broadcast advertising context? If it's operational analytics, what are the key metrics for the operational analytics? Is it accuracy? Is it some other measure of dollar value? Or is it model deployability? So those are some random and haphazard thoughts that I think are the most valuable part of my 2-day predictive analytics course. You may disagree, and I think a number of the people who voted with their feet probably do it likewise. But I will now open the question to you, the floor to you and your question.
Thank you for the presentation. I was a bit surprised to hear that you mentioned that you use a lot of the machine learning methods to actually interpret the importance of variables.
Yeah.
I'm not an expert, so I'm a little bit getting this. I have more like a bit of a mathematics background. But one of the issues I found that the variables is a way to get from some of the methods actually change every time you run the model. And if you can maybe rank order them, but not actually compare them or interpret them out of the context. So, in this sense, what is your experience on this? Thanks.
Sometimes you're right. Look, every data set is different. If you've got an extremely noisy data set, we can be debating as to whether there's any signal in there at all. And you're right, taking different subsamples of data will probably give us completely different rankings of the variable importances. Sometimes you've got very, very low noise data where the signal is clear as day. And the story is quite consistent. I think what you're saying is that any story that's told has an aspect to it which I didn't cover in this presentation, which is uncertainty. I sort of glossed over it when I talked about cross-validation and resampling. But it's always important to understand how certain or how likely or how sort of probabilistically diffuse the insights are. And if for example, you're taking different bootstrap samples of your data and you're getting different variable importances each time, I wouldn't trust them. If I'm getting the same variable importances each time from bootstrap samples, I trust them like gold.
If you're partly interested in really what.
And I would think every model has a purpose, right? If you actually really make me interested in what is driving the effect instead of the outcome, wouldn't it be better to use structured models?
Well, let's say we're doing financial trading. And as I said, the question with financial trading is there no signal or is there a tiny, tiny, tiny signal? And my experience is that with a random forest, I shrug my shoulders. With a support vector machine, I shrug my shoulders. Maybe I see something. With a linear model or a decision tree, a simple sort of relatively structured model, I find nothing. So when you have an extremely noisy, extremely complex data set, you want to take the best shot you can. And the best shot you can is usually a more sophisticated model. The other thing is that the structure can also, in a sense, lie by oversimplifying. So sometimes you can have you can have data that's fundamentally centered surround. You can model it with a linear model. It'll give you some level of predictability, it'll also be completely wrong. I will always start with something like a random forest to get a baseline accuracy. I may then build a structured model like a decision tree or a linear model and see what the difference in the accuracy is. If the difference isn't very big, I know to trust the more structured model. And maybe I'll throw the complex model away at that point. So you use a bit of both, and you use one to kind of gauge the other.
Thanks.
Probably time just for one more question. There we go. Just give me that mic.
Just one question. Models are classified in different families, right? But how hard is it in real life when you implement them to combine two of them and then get a better accuracy?
You're talking about combining models to improve accuracy.
Yeah.
Well, random forests are an example of what you call an ensemble model. It's actually a whole lot of models which are individual trees combined. There are actually a whole set of methods such as boosting, bagging, stacking, which are methods that are actually combinations of methods. And in fact, I should mention I also run an apprenticeship program, so there's a couple of people in this room who happen to be apprentices of mine. And one of my apprentices who's not in this room has recently written a package which does generalized ensemble modeling, allowing different kinds of models to go into ensemble. So in a random forest, everything's a decision tree of a particular kind. In Gensemble, you can have different kinds of models. How hard is it? I think it's currently industry best practice. If we consider neural nets to be an ensemble method, and arguably they are as well, then deep learning or deep belief networks, which are currently the best practice in the field, are also an ensemble method.
Okay. There probably are a lot more questions, but I think Eugene will hang around for a while, and please feel free to approach him. So I'd like to just ask everybody to give a round of applause for Dubossarsky for sponsoring that, the two great speakers. So I am looking for speakers for next month, so if anybody has something that they want to speak about, please come and approach me. We're also looking for sponsors for next month, so please come and approach me if your company can sponsor the event. It's really a collaborative effort, and if everybody can be involved, then we can really build up the knowledge base and make this another great meetup. But otherwise, we'll see you in May. So thanks very much for coming along. See you in May. See you later. Bye.